Okay, so today I'm going to be talking about the Bohr model and atomic spectra. Okay, so that's Bohr right there, Niels Bohr right there. He was actually the professor of Oppenheimer. I think it was at Cambridge or Oxford. I'm not actually entirely sure. But essentially, he came up with this model right here called the Bohr model. This was an early model of the atom that explains where electrons are arranged, right? In theory, electrons are arranged in orbits circling around the nucleus, right? At different energy levels. And if an electron were to drop, say from the third to the first, so if an electron were to drop from N3 to N1, it would release a specific amount of energy as light, right? So a photon will be emitted as light, energy as light, and depending on whether it drops from 3 to 1 or 2 to 1, different energy levels will be released. So 2 to 1 will be much less energy compared to if you were going from 3 to 1, right? Kind of makes sense. Alternatively, if you were to go up the ladder, right? So think of it as a ladder almost. If you were to go up the ladder, up the orbits, you would be absorbing energy, right? And so how does this relate to atomic spectra, right? Or the hydrogen emission spectrum, because this is specifically for the hydrogen atom, what I'm showing you guys right here. Essentially, there is this equation, which I will get into in a second, but that will calculate the amount of energy a photon will release. So this spectrum kind of explains which wavelengths correspond with which colors. So like I said, depending on the energy levels, some may show up on the spectrum, some may not. So if each photon is releasing a different type of wavelength of light, it may or may not show up on the spectrum here. So if a photon released a wavelength at 656 nanometers, it would show up as red. If it showed up as, if it was 434 nanometers, the wavelength was 434 nanometers, it would show up as blue. So essentially, this was just demonstrating why certain photons emit certain wavelengths and how to actually calculate which photons will release what wavelengths. The way that we calculated this was through the Rydberg equation and the Rydberg constant, right? Essentially, the Rydberg equation was just to get the wavelength of light or to get the energy of the photon, whichever one you were solving for. You were just doing Rydberg's constant, multiply that by the final destination of the electron. And what I mean by that is if an electron is dropping from 3 to 1, I would put 1 here and I would put 3 here. So F is for final, I is for initial. So it initially came from 3, so I'd put 3, and then it ended up at 1. Okay, and then you want to square both of those, so it would be 1 squared, and then it would be 3 squared. And then you just divide that by 1, subtract them, and then you get the wavelength of light. Remember that you want to divide that by 1 once again, and then convert that to nanometers. Okay, if I was solving for the energy of the photon, we would have Rydberg's constant, and we would have Planck's constant, and the speed of light, okay? Same idea. This is where the proton or the electron ends up. This is where it fell from, okay? Calculate all that, and you get the energy released. If you are taking an exam or if you are taking some sort of practice problem, homework, whatever, and the question is asking for your wavelength, anything about color, spectral light, especially if it's talking about nanometers, meters, you know that this is the equation that you want to use because you are directly solving for wavelength. If you are asking for the energy released, the change in energy, joules, electron volts, anything like that, you know that you are looking for the energy of the photon, you would use this equation right here, okay? And the bridge behind that is if you already know the wavelength, you would just do the wavelength. You would just do Planck's constant, speed of light over the wavelength, and you would get the change in energy, okay? So I did map out 2 problems here. I didn't cover them up, but I'll kind of go through them anyways. So the first question is asking, and I'll zoom in on this. Okay, so the first question is asking, calculate the wavelength in nanometers of light when an electron goes from the 3rd energy level to the 2nd energy level. Okay, so automatically we're talking about wavelength, so I know I want to use this equation right here. Use Rydberg's constant, which is 1.097 times 10 to the 7th. I already did some of the math here, but you can see it's just 1 over 2 squared, 1 over 3 squared, subtract them. You should get this number right here. All we're going to do is we're going to use a little bit of scientific notation. We're going to track the decimals. So we go 1, 2, 3, 4, 5, 6, because now that's a number between 1 and 10. So if we don't actually have to round anything. So it'd just be 1.52, okay? And then there were 6, so it's 10 to the 6, okay? So we converted this. Now we're going to do our math. So this is the wavelength. We calculated it right here. Now we're just going to divide that by 1. Now we have the actual wavelength right here. And it's asking for, where is it? Nanometers, okay? So all we're going to do is we're going to convert this number into nanometers using dimensional analysis. I know that 1 times 10 to the 9th nanometers is equal to 1 meter. Meters cancel out. So now I just do the math times that. And then this is the wavelength, right? So 658. Will this show up? 656. Was it 658? Yeah. So it'd be kind of like a deep red, I believe. Okay. All right. So the next question, super simple actually. A lot less steps, honestly. Is calculate the energy released in joules when an electron goes from the 3rd energy level to the 2nd energy level in a hydrogen atom. Okay. So we're talking about energy here, so this is going to be the equation for energy. We have Rydberg's constant, negative Rydberg's constant. We have Planck's constant, and then we have the speed of light. Same thing. So 2 was the final destination of the electron. 3 is where it initially came from. It came from 3 to 2. Honestly, you can just plug this into the calculator like I did, and you'll get your answer. Make sure you're using your parentheses. So this is going to be a long equation. So Rydberg's constant, Planck's constant, speed of light. Make sure that's all in parentheses like that. And then same parentheses around here, right? So I did some of the math already because 2 squared is 4, 3 squared is 9. So I just do the math here, plug that into the calculator, super simple, boom. And that's your answer right here, okay? That is going to be your energy in joules. Super simple. The biggest thing to kind of grasp is the relationship between the Bohr model and the atomic spectra. Other than that, if your professor lets you have an equation sheet, that's fantastic. If not, I definitely recommend that you kind of learn how to use these. But other than that, that is all this video is going to be about.